Hello. This lecture will cover pages 195 through 198 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on Chapter 12E, Bode Plot Example Number 1. We're going to do about 7 or 8 different Bode Plot examples, and we're going to start on page 195. And I'm going to keep the videos relatively short. I'm only going to do one example per video. And you're going to need about 10 sheets of semi-log paper, and you're going to need a straight edge and a couple sharp pencils as we go through this. Starting out on page number 195, I want you to take a look at our first example. It's a simple RC circuit. And what we're going to calculate here is the output voltage based on the input voltage, and everything's in terms of S. So V out of S is equal to, by the voltage divider rule, V in of S times the reactance here, divided by the sum of the resistance and the reactance. We know that the reactance is 1 over j omega c, and we're going to let S equal j omega as a complex variable. That's all this does, is just let S equal j omega to simplify the appearance of these transfer functions right now. So we know that the transfer function then, if we form the ratio V out over V in, is just the reactance divided by resistance plus reactance. And I told you, you should be able to go straight from the circuits to this transfer function. This transfer function for this circuit is this reactance divided by the sum of these two, the resistance plus the reactance. That's the voltage divider rule. Making the substitution now for X sub C, it's 1 over CS, that's the reactance, divided by R plus 1 over CS. Simple algebra. Forming the transfer function in a time constant format, it's 1 over RCS plus 1. I'm keeping the R and the C variable at this point. I'm not going to put in the final values to the values of R and C until I get to the last step. So the break frequency form, okay, if you look at it here, is 1 over S sub B, 1 over S over omega B, the break frequency plus 1. You know that the time constant here, 1 over the time constant is the break frequency. It's 1 over RC. So that's all I'm doing up here is substituting in, bringing the RC to the denominator, and I get 1 over RC in the denominator. It's just the break frequency. I like to look at it, the time constant form, I like to look at the time constant form in this format because what it does is it allows me to pull out the break frequency. But keep in mind, we referred to this here back, you know, this is really this is the break frequency, but if you invert that break frequency and put it up as a coefficient on X, it's just the time constant. You have to get used to that, either looking at it either way. But this is probably the easiest way to look at these transfer functions. So I can pull out the break frequency right here. That's in the format that we want, the time constant format we want. We can see that 1 is the constant. So if we look down here, K sub 0 is equal to 1, therefore the dB is 20 times the log of 1, which is 0 dB. That's the contribution from the constant term, 0 dB. And the first break frequency is the only break frequency. It's 10K radians per second. It's a pull, and we know pulls break down at minus 20 dB per decade. Well, keep in mind, this form we have up here, we called it case number 3B. This form of the transfer function like this is case 3B, and you might want to look back on page 194 on the previous page, and you'll see that that is case 3B, and we already discussed that the pull breaks down at minus 20 dB per decade. So at this point, we're just using that. So what we do is we go to our log paper, and notice what I did was I rewrote everything down on the log paper. Our transfer function, the contribution of the K0 term in dB, and the single break frequency was the only break frequency at 10,000 radians per second and broke as a pull breaking down. So I go back here, and the first thing I want to do is I want to set my dB axis somewhere between the top of the paper here and the bottom of the paper, because this vertical axis is going to be dB. And I know the general shape of this. If you take a look at page 195, the general shape of this is you're going to come across at 0 dB, and then at 10K radians per second, you're going to break down. So this is going to be 0 dB, and you're only going down from there. So what I decided to do is put my 0 dB up here. and every inch was 10 dB. So if that's 0 dB, I put a minus 10, a minus 20, a minus 30, and a minus 40. So the contribution from the K0 term, if you look at it, is 0 dB. So you take your log paper and you label your vertical axis, and you notice the 0 dB is the contribution from the K0 term. So you just dash a line the whole way out here, showing you your contribution from your K0 term, which was 0 dB up here. Now what about the omega axis? This is not frequency axis down here, it's omega axis. Well, we know the break frequency is 10K radians per second, so I put that somewhere, toward the beginning here. I usually go one. My first break frequency, I usually move in two divisions here. I move in 2 divisions from the top up here. 1, 2, and I label that my 10K unity point, if you will. And then I go down one scale, I get 1K, and I go down and I go 100. And I go up and I get 100K. And I go up and I could get, if I want to, 1 meg, but we're not worried about that up in this area here, so I didn't label it. So what happens at omega 1, the break frequency? Well, at 10K radians per second, the pull breaks down at 20 dB per decade. So I simply go out, I put another dashed line here on your log paper, and when I get right to 10K radians per second, that's what it is up here, it's at 10K radians per second, I label these log divisions down here at the bottom of the paper, even though they're listed up here at the top. I break down at 20 dB per decade. Well, how do I get that in there? Well, I move 1 decade up, which from 10K at 100K, and I come down 20 dB, and I put a dot right there. And there's my 2 points from here to here. And I get my straight edge. Once you get your straight edge and you line that up, you put a dotted line in from that point down to here. You put a dotted line in from here the whole way down through. And that's your 20 dB per decade slope. So I mark this at a 0 slope up here, and at that break frequency at 10K radians per second, and I label all that down here, I get a roll off of -1. That's the shorthand notation. We know a -1 is a minus 20 dB per decade. So you can see my response goes over. I darken the line in now. I only had dashed lines to this point. Well, my actual response is the sum of the two, the constant term and its contribution to the overall function, and my pull and its contribution. So I darken in the line over to 10K radians per second, and then I darken the line down, and that rolls off. You can see that's a low pass filter. And that's my magnitude plot. So what I'm able to do, I'm able to pick the dB of this particular transfer function. I can pick I can pick a frequency, and at any frequency, I can read the dB. We're going to see that in a minute. And then I do my phase plot. My phase plot's laid out in degrees here. And I put the exact same radians per second angular velocity at the bottom as I did in my magnitude plot. I put 10K 2 divisions in because that was my first break frequency. And I get down a decade, and I get down another decade, and I label these. I go up a decade, and I label them. What's my contribution from the K0 term? Well, the K0 term is 1 and an angle is 0. It's a real number. So I put a dashed line in to start out the whole way across at 0 degrees. And I labeled this plus 45, plus 90, and minus 45 and minus 90. This is phase on this vertical axis. So my contribution from the K0 term looks like that. So right now in your log paper, you just have a dashed line from this point the whole way to this point. You can never get DC down here. The frequency gets smaller and smaller and smaller. So there's no DC point on this radian frequency scale. And at the break frequency, it's a pull. At 10K radians per second, go back and look at the transfer function. It's a pull. And we know pulls are at minus 45 degrees at the break frequency. So I come down, I put a dot right there. And as a rule of thumb, we use this in our analysis. couple of lectures ago or a lecture ago, what we do is we go 1 decade below the 10K radians per second, and that gets us at 1K radians per second, and the contribution from the pull, it hasn't started contributing to the overall phase shift yet, so you're at 0. And then I go a decade above, and a decade above you get your full effect of your pull. So it's at minus 90 degrees because we know pulls phase from 0 to minus 90 degrees because they're in the denominator. At the break frequency, they're at minus 45. So you draw your asymptotic line in through 45, the negative 45 to this point. So there's your phase angle. So now you got your phase plot and you got your magnitude plot. And I want you to notice these are the asymptotic lines that the actual curve approaches. In actuality, if we go back here, at the break frequency, you'll be down 3 dB, and you'll see that in your calculations. And everything's asymptotic to these lines here, the actual curve. So the actual curve is under that break point at 3 dB, and then approaches the 0 dB axis here, and it approaches this roll-off of minus 20 dB per decade as it goes here. Now that I have both of these magnitude plots, the magnitude plot and the phase plot, I want to show you the power of the Bode plot. And that takes us to page 198. We're going to use the Bode plots to find the voltage gain in dB at 40K radians per second. And we're also going to, at 40K radians per second, we're going to find what the phase shift is from input to output. So I want you to very carefully, it depends how accurately you did this. The more time you spend here, the more accurate you can get. I want you to look at this magnitude plot, and I want you to find 40,000 radians per second, which I find right at that point right there. That's 10K, that's 100K. You have to look up above here to see where that's at. And you come down or you come up, whatever you label. I usually label this 40K right here if I'm trying to find something at 40K. And if you come up to that point and you come across, I want you to read whatever dB you get on your curve. I got minus 12 dB. And then I want you to take your phase plot. And I want you to look at 40K. 40K is going to be right here. Right there. Again, I have to look up above. That 4 represents 40K up above, and I can come down, and that's the 40K point at that point. And I want to come over, and I want to read the phase angle. Well, the way I have this laid out is there's 10 divisions between 0 and minus 45. This is per inch. And there's 10 divisions here between minus 45 and minus 90. That's the way these all get laid out. So the midpoint is 22.5 degrees between the minus 45 and the minus 90. Each one of these sections here, each one of these points as you go through here represents a 4.5 degrees. If you take 5 times 4.5 degrees, you're going to get that midpoint at the minus 45 minus 22.5. So you're going to be at 67.5 degrees, minus 67.5 degrees when you get down to this point here. You can just go ahead and interpolate this. But if you try to read the angle at 40K radians per second, and you come up and you find whatever that angle is right there, I want you to try it on your graph. I got approximately, and just approximate this, I got approximately 72 degrees, minus 72 degrees. Now I want you to calculate the actual values using the transfer function. So I go back, and here's my transfer function. We know S is just J omega. The 10K is the break frequency. It's not going to change. So I'm evaluating the transfer function at J40K. I mean, that's where we evaluated the Bode plot. So let's see what we get. So I just substitute in for S J40K. That's all I'm doing here, this transfer function. Every place I see S, I see a J40K. I get a rectangular form down here. This is the imaginary part first, plus the 1. I just flip that around. I end up with my transfer function at J40K is 0.243 at an angle of minus 75.9 degrees. Follow that through and see how I did the algebra. That's my transfer function. There's my gain. But we need to get that in dB. That's a 0.243. So I take 20 times the log of 0.243. I get a minus 12.3 dB. That's the actual value. That's exactly what the value, that's the gain at 40K radians per second. And the angle is simply what you get here. It's minus 75.9. Now, there's a little bit of work to go through this, but I want you to compare the gain at 40K radians per second actual to what we got off the plot. Pretty doggone close. And look at the actual phase, minus 75.9, and I'm pulling off minus 72. Again, very, very close. You're going to find, if you take your time with these Bode plots, you don't have to go through all this algebra. That's the beauty of the Bode plots. You can use straight line approximations to come up with the dB gain and the phase angle at any radian frequency. And you don't have to go through the algebra. I want you to go ahead and try to read off the graph where you would be at voltage gain and dB at exactly at the radian frequency. And look at the graph and the phase and see where you're going to be, the phase. You're going to see you're going to be at minus 3 dB at 10K radians per second. And you're going to be at minus 45. Now, I'm using a little bit insight when I read the Bode plots here, because remember what I told you. The actual curve, one person may say, well, at 10K radians per second, you're at 0 dB. Well, remember, that's the approximation. But when you're right at the break frequency, you can use that. You know you're going to be exactly 3 dB down on the actual curve. So I just subtracted 3 dB here. And that's how I got my minus 3 dB here. And then my angle, you could see if you look at the phase at that break frequency, you're going to be at minus 45 degrees. That's pretty easy. It's right at that point. The actual curve here is the actual phase curve is asymptotic at this point. It comes down, it crosses over here, and then it's a little high on this point down here. Because it's asymptotic to this line, it's asymptotic to this line. So you have to picture that actual curve of phase coming in, going above here, rolling off, coming below here, rolling off, crossing right at minus 45 degrees at the break frequency, and then coming above and being a little high down here. But these aren't 3 dB points at this point and this point, because that's angle over here we're talking about. So you can do very good approximations. And then I want you to go ahead and do what I did up here. Find the actual value. Go back to the original transfer function and substitute in J10K at S. There's a little bit of work involved there. And you're going to see that you're very, very close. Matter of fact, you're going to be exact. You're going to be exact in both cases here. Bode plots are definitely the way to go. That's example number 1. And that concludes this lecture.